using that as a tool to see where you're at. What we have to go over today, and again, one of the reasons why you had water involved in the bagging activity is we can dissolve ionic compounds in water that allows them to react as a solution much easier than they would if they were in their solid state. So to remind you about ionic solutions a little bit, but then reactions that involve ionic solutions is probably the bigger thing that we have to go over here today. Now, when you take an ionic compound and dissolve it in water, it would become an electrolyte solution, which is something that can conduct electricity. I mean, when you drink Gatorade after a workout, it's to replenish your electrolytes. Oh boy, are we ready, AP Bio people? You know, we got enough sodium and potassium there for those sodium potassium channels so those neurons can fire effective signals across synapses. Does that sound kind of vaguely right? I think I remember my bio. When an ionic compound is dissolved in water, much like when I went over this with your test, it breaks up into its ions. That's called dissociation. So that's just a term I want you to be aware of, as is this last term. Hydration is referring to an ion being surrounded by water. Now, why did sometimes the baggie feel hot, sometimes the baggie feel cold? It's a combination of two things. One is chemical reactions can sometimes be endothermic or exothermic. So, you know, does it feel hot? Oh, it gave off heat. It's exothermic. Does it feel cold? It's endothermic. However, dissolving itself can also be endothermic or exothermic. And the way that the new sequence is set up, we're not going to really experiment with that until second semester, early on. So we talked about the process of dissolving in the last unit, but the heat associated with it, we're going to go more into next unit, so that's the beginning of next semester to go over. But to dissociate, second to last term here, means you are pulling apart two things that are attracted to each other. Well, that takes an input of energy. Hydration, however, is when water in its polar ends are naturally attracted to the ions. That would release energy. So between input and release, whichever one is a bigger value, would help determine as well whether or not it feels hot or feels cold. So part of me is a little skeptical on them saying that, you know, temperature change is an indicator of a chemical reaction, because dissolving itself can give off or change temperature. So remember, Na plus Cl minus surrounded. I don't think I have to draw that one out necessarily for you. So slide one is just a few vocabulary terms to remind you about an ionic solution dissolved, or an ionic compound dissolved in water to make a solution. What we have to go over today, now that we're starting a reaction unit, reaction unit is what happens with reactions involving these things. For example, the calcium chloride could dissolve in water pretty easily to make a solution that allows it to react better with the baking soda. The baking soda also could dissolve in water. So, precipitation reactions. These are reactions that form an insoluble product. There is a little table on this slide on the bottom right that hopefully brings you back to the good old days of Chem 1, where if I gave you reactants, if you figured out the products, if one of those two products was insoluble in water, that would be an indicator of, hey, that creates a precipitate. That is a chemical change. That is a reaction. I believe when I sent you, boy, ranking of so long ago now, that little envelope that I sent you this summer with all the goodies of naming and whatnot, I believe on one side of the polyatomic ion sheet was a solubility table. If there wasn't that, bless you, feel free when we're working today to grab one of these. So if you need that as a reference, that's perfectly fine. However, a couple of things to remind you of. First off, that table shows you, again, what's soluble in water, what's insoluble. If you're insoluble, you created the precipitate. Thus, you are the indicator of a chemical reaction. Ions that are soluble, I'm almost using too many negatives, they are not insoluble, so are soluble, are spectator ions. Remember, spectator ions are the ones that are there at the start of the reaction, they're at the end of the reaction. I know, for example, with your Beatty experiment, sodium would have been a spectator ion every single time. Sodium is soluble in water, no matter what other anion is around. And that's something that you're going to need to be aware of as well. So my last point isn't really something you have to write down. When I say know the common soluble ions, why I say that is today if you want to use this table to help out, great. However, you do not get a solubility table on the AP exam, and you won't get it on any test that I give you as well. So what we need to realize is typically problems are picked that you should be able to look at the products and know right away, oh, that can't be the precipitate because it's an alkali metal. Because lithium, sodium, potassium, those alkali metals, they do not create precipitates. Nitrate, NO3 minus, is far and away the most common anion that doesn't create a precipitate. In Chem 1, we had you highlight the I's. I know I called it playing battleship, where this and this come together. Is it a hit or is it a miss? But there are some rows on here and some columns that never are a hit, because some things are always soluble. Typically, these have low charges. The higher the charge, the greater attraction two things can have to stick together to create a precipitate. But if it's plus ones and minus ones, a lot of times there isn't enough charge. Not always the case, but a lot of times there are. So through the course of today, when you're doing practice problems, when you're looking at that solubility table, I would suggest to you to, know how to read that table, but at the same time, recognize those ions that are not going to create a precipitate. One of the most common examples of a double displacement reaction is lead 2 nitrate potassium iodide. What I would like to do is remind you how to write a balanced equation, an ionic equation, and then one of the goals of today, the net ionic equation. And as I wrote down here with an asterisk, this is very commonly asked on the AP exam, is to write the net ionic, because we are not concerned about spectator ions. They're just there. They don't do anything. So, let's start off with the balanced equation. Lead 2 nitrate. Remember, we have to know some of our polyatomic ions as well. This is PbNO3 2. And that would be aqueous. Plus, the other reactant was potassium iodide, Ki. I am not taking reaction types slow with you. I'm not going to spend an entire day going over here are the 5 types of reactions we did in Chem 1. I'm hoping that I can just briefly go over these and remind you of what happens. This is a double displacement reaction. The way we can recognize that is we have 2 compounds. Recall in the double displacement, the cations will switch places. Now, when they switch, you have to rebalance formulas. What I mean by that is lead's a +2, potassium's a +1. So when they switch, the potassium's now with nitrate. But that's not KNO3 that's just going to be KNO3. I'll save phase notations for a minute. So when lead, which is a +2, goes with iodide, that's PbI2. So again, when we write balanced equations, make sure the products are written out, balanced appropriately. Now the equation as a whole should be balanced as well, because notice I have 2 nitrates on the reactant side I can put a big 2 to have 2 nitrates now on the product side. But now I have 2 potassiums on the product side. A big 2 here balances my entire equation. The only thing that I have not included yet to finish this off is the phase notations of the 2 products. In order for this reaction to actually occur, a precipitate needed to be made. I mean, it could be a pure liquid as well, because your acid-base reactions do that. It could be a gas. You saw gases created as well more often than you saw precipitates today. But I need something that isn't aqueous. You could either, again, reference this sheet and play Battleship. Which one makes the insoluble substance? Or, general rule of thumb, nitrates are always soluble. Alkali metals, always soluble. That means this is aqueous. This is going to be a solid. This reaction is often shown in textbooks because you start with 2 clear liquids, lead nitrate, potassium iodide, and you make a yellow precipitate. Till recently, we used to do this reaction in this building. However, lead ions are a pain to dispose of, so I got rid of all of our lead because I didn't want to deal with disposal of it anymore because it can't just go down the drain. If that's your balanced equation, in Chem 1, we also went over a total ionic equation, which a total ionic equation is recognizing when I write an ionic compound and put AQ after it, it is ions floating around in solution. For example, PbNO3 would be Pb with a +2 charge floating around and 2 nitrates floating around in solution. Recall that I'm writing lead as a +2. It's very common to see it as a 2+. I don't care which order you put that in. Technically, I probably should be calling it 2+. There's a difference between an oxidation number for a covalent compound and an ionic charge of what goes first, the plus sign or not. But I've asked AP and people before, and they don't care what order you put that in. As long as you show a charge, they're happy. Does this look familiar to us? Again, for some of us, it's been a year and a half ago. I understand if it's a little foggy for us. To separate out the Ki, make sure you distribute that 2 to both things. So I have 2 potassium ions floating around and 2 iodide ions floating around. What this version shows is here are the 4 possible ions that are all floating around. Then some of them are going to come together to create a precipitate. Now when I look at the products, my KNO3 is aqueous, so I have to continue to show that that is broken up. I distribute the 2 to both parts. However, the precipitate, the lead-2 iodide, is the thing that's stuck together. That's that cloudy solid that's created when 2 solutions come together. That doesn't get separated because it's not aqueous. I'm running out of room, so I'm just going to write it right below. Plus PbI2 solid. This would be a total ionic equation. The balanced equation is more of a summary of what's happening. This is a little bit more specific of I have this ion, and that ion, and this ion, and that ion, and it makes these ions plus the precipitate. But going back to one of the goal sheets for the day, a net ionic equation is the most common thing to be asked to do. Quite frankly, it's pretty common to be given a balanced equation on an AP question. So they'll give you this top one frequently, and then they'll ask you to write the net ionic. So some of us, again, a little bit worried about nomenclature at times. Again, maybe we don't have to worry about that as much, realizing that it's common that you're given some of this information. A net ionic equation gets rid of spectator ions because spectator ions don't actually do anything. They're there at the start, they're there at the end, but they're not contributing towards the change that makes it a chemical reaction. For example, I see two nitrates on this side, I see two nitrate ions on that side. That's a spectator. So is the potassium ions. The other things are different start to finish because they're aqueous to begin with, they're solid to end with. So my net ionic equation is lead 2 ion plus 2 iodides makes the PbI2 solid. Again, today, if you need to grab a solubility table, if you don't have one in the back of your polyatomic ion sheet, just grab another one for me here. That might help out in this. I have one more slide to go over then, because what we didn't do in Chem 1 is address the fact that this method of balanced total ionic and net ionic can not only be done for double displacement, which is two solutions mixed together, but it can be done for single displacement as well, which is a solution and an element. So that's what I want to wrap up with here. Single displacement is a solution and an individual element. And again, I'll show you an example of this in a minute. Recall in that half a sheet of paper, not only is there a solubility table, there's also an activity series. The activity series is a ranking system of what things are more reactive than others. This typically would not be given to you. However, memorizing of this, usually you can get away without doing that. Notice you have like alkali metals and things like that at the top. Transition metals towards the bottom, silver, gold, platinum. There's also an activity series for halogens, but at the same time, fluorine is the most electronegative halogen, so it is going to take part in a switch at times. What you have to remember from this activity series is if the lone element, in the example I'm going to give you, copper plus silver nitrate, which is one we did in Chem 1, if the lone element is more reactive than the element within the compound, the switch will occur. Notice how copper is higher on the list than silver, so this reaction will actually occur. So again, I want to run down how to write this equation for copper plus silver nitrate. As an equation, an ionic and even a net ionic. And then that'll wrap up our notes. You have a practice sheet to practice this for about 10 or 15 minutes to wrap up class. And that's our day. So, start with my balanced equation. Copper solid plus silver nitrate solution. Again, how do I recognize it's single displacement? I have an element and a compound. Synthesis would be if I have one product made. Remember, you synthesize something, you make one thing. Decomposition is where you have one reactant and it breaks down into more than one thing. It decomposes. Combustion reactions are our burning ones. We actually showed you a little bit of that in Unit 1 with our empirical formula stuff. Some sort of carbon-hydrogen compound burns in oxygen. Your web assignment for tonight is going to mainly deal with the ion part, but I did sprinkle in a little bit of just, hey, do you know what a synthesis reaction is versus decomposition, things like that as well. This switch, it can make solid silver. Now, the one thing that you might not have known is when it makes copper nitrate, it makes copper 2 nitrate because it's a blue solution. And again, to balance this equation, I'd put a 2 in front of the silver nitrate and I'd put a 2 in front of the silver. This would be a balanced chemical equation. Total ionic. Well, I have solid copper. That has no charge. And that's actually one of the reasons why this reaction occurs. Elements are more stable if they have a charge, because they're more likely to have a full octet by either gaining or losing electrons. So whatever's more reactive is more likely to obtain that charge. I have 2 of the silver ion floating in solution, and 2 of the nitrate ion floating around in solution. Again, make sure when we are writing ionic equations that we are showing charges. This would make 2 silver, which is a solid, plus, I'm going to kind of stagger my writing so I can fit it on one line here, a copper ion and 2 nitrate ions. Again, that is showing which ions are floating around solution and the solids that are present as well. You might even recall that this type of reaction was commonly used for an oxidation and reduction, or redox reaction. Because really what happens in the mechanism here is there's an exchange of electrons between the copper and the silver ion. We will remind you of redox in this unit. Net ionic. My spectator ion in this particular reaction is the nitrate. Nitrate doesn't do anything, ladies and gentlemen. It's just there. Back in the semester 1 project or semester 2 project in Chem 1, if you had a test tube that only had cations in it, I just had nitrate as the anion because it wasn't going to show up on any single test. And it wasn't going to precipitate ever. It was just the perfect anion to use for that. What's really happening in this reaction is solid copper is reacting with 2 of the silver ions to make solid silver. And now a copper ion. Ionic equations are used for solutions that are ionic. And that's going to fall in the single displacement and the double displacement categories. So today's goal was to go over that, give you time to practice that now. And again, WebAssign you'll see a little bit along with just other general naming. So